Hi, my name is Mario, and I'm here to present the work mechanical properties analysis of a pigment-free epoxy Novolac reduced graphene oxide composite coating through TD-NMR. So, I'm a PhD student in chemical engineering, materials, and environment process in PUC-Rio. My master was in materials and chemical and metallurgical process engineer, also in PUC-Rio, Brazil. And we developed the project properties of polymeric anti-corrosive coating, non-activated with graphene. We have performed characterization tests for nanomaterials such as XRD, Raman, AFM, DNA, and a lot of corrosion tests like cell immersion and accelerated cyclic testing. I was a FAPES student, grade 10, during my master degree, and I graduated in petroleum engineer from the University of Vila Velha, and I worked in the industry from 2012 to 2016 as an operations engineer at Halliburton Services. So here we have to discuss first the importance of a corrosion stud. So the degradation of metallic materials by corrosion is an important issue for the industry due to production shutdown, loss or waste of valuable sources and resources, contamination of products, less efficiency in industrial process, and costs in process maintenance. So according to ANSYS technical report, this annual cost worldwide is estimated in $2.5 trillion. Bringing the subject to the oil and gas industry, we can justify a corrosion study because the potential risks of accidents and explosions, more than 60% of leaks on board, are due to corrosion or fatigue in equipment and structures. So here we have the corrosion prevention. So the use of protective coatings on carbon steel is one of the main techniques for the prevention of corrosion phenomena. These coatings can be organic, like paints, resins, or polymers, inorganic, cement, and among others, and metallic. The epoxy resins are one of the most commercialized coatings in the industry, given their thermal and chemical resistance, compatibility with a large number of materials, good adhesion, and others. In the present work, the novelty compared with previous work is the fact that the organic coating studied was an ink, which is basically composed of a Novolac Type 2 industrial epoxy resin, however, without the addition of pigments and fillers. So here we have a figure showing the coating, that is your polymeric material, the resin, between the electrolyte and the metal that we're going to protect. The polymer coating deposited on the metal substrate was an epoxy Novolac based, manufactured by WAG Tintas, WAG Resin. In the specific case of this work, the company provided resin without solids, no fillers, and no pigments, so that the effect of the nanoparticles on corrosion tests could be studied in isolation. Coatings component A consists of a bisphenol F and phenol formaldehyde, and component B is a polyamine-based curing agent, as we can see here in this slide. So the graphene used in this work was chemically synthesized by oxidation and reduction of the commercial graphite micrograph. Graphene oxide was obtained by chemical exfoliation of the graphite using the method employed by hammers. Graphene reduction is achieved by direct action of ultraviolet radiation for 5 hours indoors, resulting in a liquid and reduced graphene oxide sample. Here we have the results of TD-NMR experiments before tensile testing, and we can observe that the addition of graphene provides an increase in the mobility of the polyamine matrix molecular dynamics, especially in the semi-rigid and mobile regions, with an increase in the transverse relation times. However, the rigid fraction does not show time and percentage variations, indicates that the mobility conferred by graphene occurs preferentially in the regions of the matrix where the chains have greater mobility and space for discharge to be allocated. So the results found by OW4 indicate again a mobility in the resin matrix in the same rigid region, with increase in the T2 value for the main domains in addition to the presence of smaller domains close to 100 milliseconds for the composition containing graphene. From the distributions, we can see that the mobile region of the resin, the chain segments with T2 of 7 milliseconds are greatly influenced by the presence and the concentration of the graphene, dividing into new relation domains with higher T2 values in increased width, especially for the sample which have 0.5 of graphene. This indicates that in addition to the mobility gain, the graphene filler also increased the number of different conformations of chain segments in the polymeric matrix where the density of the cross links is smaller or where chain ends are present. The results of a longitudinal relation also are shown in this figure. This relation is sensitive to morphological change for spin diffusion paths of the order of 20 nanometers, while the transverse relation detects fluctuation in smaller segments. So it's possible to see the brittle behavior of the neat resin here in the results of the sensitivity testing. So the EPCR without graphene elongation is about 0.35%. The sample, which has 0.1% of graphene, followed the semi-brittle behavior closely, with a slight change in the curve. So the elongation has increased to 1.6%. In the sample which we have 0.5 of graphene, the behavior is completely different. The material is found in a transition state between brittle and ductile, with great increase in elongation, up to 3%, and great decrease in fracture strength, in about 64%. So apparently, the addition of 0.5% in weight of graphene led to a more flexible material. And here we have the same results of TD-NMR experience, but now after the tensile testing in the epoxy resin. So analyzing the behavior of the samples after the mechanical test, it becomes evident that even after mechanical stress, the compositions containing graphene have shown greater mobility as a function of the filler concentration, especially in the mobile region, while the rigid fraction is practically unchanged. The O44 results display in more detail in relation to the MSE FID, a tendency of T2 reduction in the same region of the samples containing graphene, mainly found the sample that we have 0.5% of graphene. So, however, for the region of high mobility analyzed for CPMAG, a mobility gain behavior is observed as a function of the graphene concentration even after the deformation of the material, with new relation domains appearing have with relation times of almost 100 milliseconds for this 0.5 addition of graphene. So, the conclusion is that the molecular dynamics of the samples, both before and after mechanical assays, was described using TD-NMR pulse sequences that allowed the observation of high, intermediate, and low mobility dynamics of polymeric chains of the epoxy matrix. The results suggest that the addition of graphene oxide sheets may have been responsible for the expressive change in the mechanical behavior of the epoxy. So this experiment suggests that the nanoparticles were deposited in the regions of intermediate and high mobility, where there is a lower concentration of cross-links between the polymer chains. This preferential location extends over segments of at least 20 nanometers in diameter, indicating a small tendency for these particles to agglomerate in the polymer matrix. Furthermore, the presence of graphene oxide sheets spread over the regions of high mobility may have facilitated the chains sliding during the mechanical load, leading to the observed behavior. So I want to thank you, the SENS, Laboratório de Investimentos Anticorrosivos of Petrobras here in Rio de Janeiro, Brazil. Also, I have to thank you, IMA, Instituto de Macromoléculas, Professora Luísa Mano, in UFRJ, the Flow Chemistry Nanotechnology Group of the Chemistry Department in PUC Rio, the Nanotechnology Lab, University of Brasília, CAPES, Coordenação de Aperfeiçoamento Pessoal de Nível Superior of Brazil, and FAPESG, Fundação Carlos Chagas Filho de Amparo à Pesquisa do Estado do Rio de Janeiro. So here are my contact info. So if you have some doubts, you can contact me by phone or send me an email, and I'm going to discuss. It's going to be a pleasure to discuss any doubts with you. Okay? So good congress for us, and thank you so much.